Second part of week 5 lecture. I never made the video because I thought that there was not enough content to talk about structural induction, and the things that were covered in the lecture were good enough. And I had covered another video for, I think, functions and relations for that, so I thought that was enough, but I received a lot of queries, and hence I'm making the second part of structural induction. And I also started to collect the thing about spring quarter instead of winter quarter because it never came to my notice. And thank you so much to bring to my notice. All right, let's jump in. Till now, what we've seen is that if we are proving statements, we always take a bottom up approach, um, like proving a predicate for all natural numbers. So first, we directly prove a base case, and then we try to begin to build up. And suppose we wanted to prove a number, like a statement p of n for all natural numbers n. Sorry. Then what happens is, we first proved a base case such as p of 1, and then we prove that for all n. So that's like, how do we do that? So we go from pn to pn plus 1, right? So we prove p of 1, and then from p of 1 we go till p of n. So we assume p of n is true, and we prove for p of n. And in strong induction we proved from p1, p2, p3 till pn, and then we proved for pn plus 1, and then we generalize the term, right? So thus we prove p1 is true and use the implication to show that p of 1 is true, that implies that p of 2 is true, and p of 2, and then p of 3. So now that we've established p of 3, we can show p of 3 since p2 just implies p3, right? In summary, the logic for proving pn is true as right here. p1 is true and p1 implies p2 implies p3, and it goes on to imply p of n is also true, and hence p of n is true. So this is what you've covered till now. Now what we're going to see is that if you want to prove p of n for some arbitrary n, right? And we know that p of n minus 1 is if p of n minus 1 implies p of n, then we should focus on proving p of n minus 1, right? So we are using the same logic but thinking of a more recursive manner right here. Suppose we have a data structure S. We want to show a property holds for the data structure, that is p of S. So this is a preposition p for on the data structure S. Suppose we have an element that belongs to S, and we need to show that the property holds. We know that it holds for the set S minus the element A, right? So then we have to show that p of S minus A implies that p of S is true. This is what we've been doing, right? You have a whole data structure S, remove one element, and you know that it holds for that. So this is p of n minus 1, and you prove p of n. Now, here look at this, that you have p of e1 is true, and you know that p of e1 implies p of e1 e2 keeps on going till p of the set S minus e3, just one element, and that would imply that ps is true. So you know that ps, you prove that the base case is true, and then you keep on building on cases. You add an element at each proposition. So this is the first one for just the element e1, right? That was right here, e1. I'm sorry, these are the same things. So assuming p1 is true, you imply that p of e1 e2 would be true, and using that you keep on going on till you have the whole set minus just e3, and from that you can prove. So if you're able to prove that, you can say that p of s also holds true. So did you understand? This is the base case, and then these are constructor cases, like you keep on adding an element till you reach the final recursion step that you want. So we see that the base case is directly showing ps holds true. So you know ps is holding true just from implications from the first base case, and then we show that implications increase the number of elements in the stack as you arrive at a stack with n elements. So this is one element set, two elements, three elements, n minus 1, and this is the final one with n elements. This is how you define structural induction. The base case specifies an initial or minimal element. The constructor case specifies how to construct new instances of the data structure from base instances or previously constructed instances, right? So base case and constructor cases. Let's do an example. If you are given so what is a binary string? So it's a string of zeros and ones, And alternatively, we can define binary strings recursively, as shown here, that the base case is the empty set, and here we are just showing it by lambda. And a constructor case is if S is a binary string, then if you add any 0 or 1, so that A dot S is a binary string. So if you concatenated A to it, it is still a binary string where A belongs to 0 or 1. So this could be 0 or 1, right? We use this definition to create arbitrary binary strings. To convince ourselves that this is a valid definition of binary strings, we can prove some properties that should be true about binary strings and only use the above definition. So let's try to use some property about binary strings and see if it is a valid binary string or not. So the length is the first case. So if you add one character to the length should increase by 1, right? So let the string be length of the string be denoted by modulo the string variable. So here it's lambda, right? So we can define the length of binary strings as follows. So this is lambda 0, base case is lambda 0, and constructor case is when a character is concatenated, that A belongs to 0 or 1, is concatenated to S, you have AS, the magnitude of AS to be 1 plus the length of S. So you just keep on adding. So this is the length. Now let's see, define a recursive operation with the string concatenation, right? So if you're given a base case S is lambda and you concatenate, sorry for the pronunciation, if you concatenate a character T, then S dot T would be T. So you added a blank to an existing string, that will still be T, right? So the base case is no character at all. Now the constructor case is if S is not equal to lambda, then S is A dot ST, where A is either 0 or 1, right? So you concatenate 0 or 1 here, and you should get the previous one, like the string is S, right? This is the constructor case. You just keep on adding a value to it and you see that it holds true. We define st as a dot st dot t. So you're just adding the value a dot st to it, right? And the function takes binary inputs, strings s and t, and outputs s dot t. Claim for us, according to the property, was that if you concatenate an empty string to an existing string, the string wouldn't change, right? So a predicate ps would be s dot lambda would be s, right? And we'll prove the property using structural induction and our definition of concatenation as we defined earlier. So proof, the base case is s is equal to lambda, and we have to show p of lambda that lambda dot lambda. So if you concatenate the same string, you still have lambda, that is when s is lambda, right? So lambda dot lambda would still remain lambda, and we know that. If lambda is s, then s dot t is t. Here t is also lambda, so s dot lambda would also be lambda as desired. So inductive case would be let s equal to 0, where a is a character between 0 from 0 and 1, and we need to show that st is implies p of s, right? So s dot lambda is a dot st dot lambda. By the definition of s, we know that, right? Now plug in t is lambda here in the constructor case for concatenation, and you have a dot st. So a dot st would be by the inductive hypothesis that s dot lambda is a dot st. Now a dot st can be written as s because that's the one that was removed. So s dot lambda is s again, right? This is how you write the structural induction proofs. I'll just go over it again, and then so this is the first claim. This is how you prove it. A base case, and you start by showing concatenated values. The second claim would be if s and t are binary strings, then prove that s dot t, the length would be the same. So you just add s, the length of s and the length of t to get the length of s dot t of the concatenated value, right? So try proving this. If you have any queries, I'll show you how to do it, right? I'll just go over it again. We started by defining what structural induction looks like. We went from here, the bottom approach, to the top up approach, and we defined what structural induction is. And we did an example on binary strings where we started to define what a binary string is, the length, and the concatenation functions. And I tried to show you one of the functions, that is the concatenation value by structural induction. and I'm leaving the showing the length property of the same binary strings to you, and this should help you with the homework. And best of luck and stay safe. Thank you.